All right, here we go. Let's take a look at the next section. We're doing velocity and other rates of change. I love this section. It's going to be a lot of thinking. Let's look at some rates of change. They're really everywhere. Let's take a look at my Facebook profile pic here. When I started, it was a really cool profile pic. Kind of had that little like blowfish boatman hat going. That was pretty awesome. Then it got even cooler. Like I'm going from cool to cooler rate of change. The surprise, like, hey, didn't see that selfie coming. Followed up by the coolest profile pic ever. The mustache creep. No, that's actually kind of creepy. That is not a good example, but definitely a progression of some kind of change there going on. I don't know how to describe that. Let's take a look at this for calculus. We're going to do some. We're going to do a couple different ways: verbally, algebraically, graphically, and numerically. Didn't fit on this slide. So what does that mean? So if I'm looking at this, let's take a look verbally. It's a sentence. There we go. So can you take this area of a circle, blah, blah, blah? Sure. You just write the equation. There it is. The area of a circle is a function of its radius. So this is no problem. This is before calculus. You could do this no problem. I like to call this BC, before calculus. So the A of 4, what does that mean? It means plug 4 into the equation. Boom. And you've got it. That just means what? When you are doing this, when the radius is 4 inches, the area is 16 pi inches squared. So that's old school. How about what I like to call after derivatives? Here we go. We've got this one. The a prime of 4 is what? So it means find the derivative. What is the derivative? So some ways I want to write this is the change in a over the change in r. So don't freak out if you see that. That's the same as a prime. Same thing is what? Is 2 pi r. So we take the derivative. Now can I plug that in here? Sure, 2 pi r. So the radius is still 4. What does that mean though? We're going to be a lot into what does it mean in labeling. It means when the radius is 4 inches, the area at that moment in time is changing 8 pi inches squared per inch. That is so weird, but that is describing how it is changing. So we're looking at the rate of change. The radius is causing the area to change. So it's slightly different. That's the derivative at that moment. And then we've looked at the average rate of change from like 3 to 5. That's the difference of finding, remember, the a of 3 over the a of 5. And then use the change in y. So that's like the secant line from 3 to 5 versus the tangent line. So that's the big thing going on here. And we could find those. We could plug in the a of 3. Let's just do it real quick. That would be what? Pi r squared. So that would be 9 pi. Minus 5 would be 25 pi. I just went ahead and squared it. And that would be all over negative 2. So we clean that up and say that's how fast the area is changing per inch. Excellent, very nice. So changing that to a graphical. So I'm going to give you all kinds of rates of change here. This is somebody heating up their kiln for their pottery. So we got their pottery going on here. So what does the h prime of 2 mean? So I don't have the equation to look at anymore. I'm graphing the equation. So I'm graphing y equals this function. So what's going on here at 2? Well, there it is. So this is the actual, if I looked over here, you know, it's around what, in between there, like 750 degrees. Celsius, but this is not asking what the h of 2 is. This is saying what is the h prime. So you got to kind of estimate it. Tell me about this. Well, it's a very positive. This is definitely a positive. So what's going on here when my derivative, the tangent line here is a pretty steep positive? That means my temperature is increasing. The h is increasing. How about the h prime of 4? What's happening at 4? Well, here is 4 up here. Well, what's going on here? What's the derivative at this moment? What's the tangent line? Well, it's flat. It's 0, so there's nothing going on. So this is no change. There is nothing going on here. Versus the h prime of 8. What is the slope of the tangent line here? The derivative is negative. So that means my kiln is cooling down. So I've got no change versus positive versus negative. Isn't that pretty cool? Could you find the average rate of change if you had to in this problem? Sure, no problem. From 0 to 3 would be what? From 0.0, it's slightly above, it had already been on or something there. Up to 3 is here. It looks like whoop, right here. So what am I finding the average rate of change? I'm actually finding the slope of this line, which was that secant line. So remember, this is back to that secant line, if I can spell secant right, versus the tangent line. So instantaneous rate of change is that first derivative. It's so nice because it tells us what is happening at that exact moment in time. So you may have to look at a graph and approximate it. What else can we do? We can look at a table. So let's say that if I'm making calculators, this is representing my profit. So I want to approximate the p prime of 9. So this means I want to approximate the profit at 9. Well, it's not on my table, so I know it goes right here, right? So you could guess it's somewhere in this range, But how do I approximate it? Well, I'm going to use the closest secant line possible. You could do the secant line between 6 and 12, but get as close as you can here. So I'm really going to say, what is the profit at 10, the change from 8 to 10? So I'm really looking at the change from here to here, over the change, that is that change, over 10 minus 8. So I'm looking at these 2 points, the change in y over the change in x. So I'm finding the average rate of change. Is it a great approximation? It's maybe okay. If I would be better, the closer I get, the better. But I'm at the secant trying to make that tangent line. So what is the p of 10? Well, it's 13.2 minus the p of 8 is 11, and then subtract those, you get over 2. Let's just finish this bad boy out. What does that give me here? That looks like that'll give me 2.2 over 2, which gives me 1.1. Okay, so what does this mean? So I've got 1.1 change in y would be the profit. So this would be every 1.1 thousand dollars. That's the y per what? Per the x, which is this case calculators, and they're in hundreds, per 100 calculators. So hopefully your handwriting is nicer than mine. But that is it. So we're really got to focus on labeling these things. This is hugely, hugely important. So it's a change in y per over the change in x. So we're going to do that. It's a rate of change. So that's approximately how it is changing at that moment in time. So we can tell it's going up. This is positive. It's a pretty good approximation of how it's changing. Excellent. How about this? The big dog, velocity. So I've got Mr. Bean here playing catch by himself, poor guy, and I'm going to give you the equation. So here I'm going to give you the equation. I went ahead and graphed it for you. So this is the position function. We usually use s for position. So if I want to find velocity, so this is the s of t. So what is the velocity? Well, velocity is the first derivative. It is the rate of change. So I'm looking at the rate of change of position. How fast is this ball moving? So the ball goes up over time. This is time on the axis. And this is what? Its position. Where are we in here? Feet, meters? We're in meters. Excellent. So we're in meters. So the ball goes up, hits its highest point, and comes back down. So if I want to find the velocity, I want to know how fast is that ball moving. So that's s prime. So s prime of t equals the velocity. So a lot of times we just say the v of t. Excellent. So can I graph this function? This is kind of crazy. What is the velocity of this ball? So if he throws this ball up, what kind of velocity does it have? Well, it actually has a what? He's threw it with a positive velocity. What's going on right here? I think this is the easiest one to see. What's the velocity right here, or what's the first derivative? Well, think about the ball. It's maxing out. It has no velocity. It went up, it stops, and then it goes down. So that is a velocity of what? Of 0. So that is going to be this point right here. Somewhere in here it has no velocity. So it started off with a velocity, it hit this point, and then now what's going on? Well, it has a negative velocity. It's actually, that's a terrible tangent line. Let's make it thicker, make it kind of hit there. It's kind of negative velocity. So here, anywhere here the velocity is positive. Anywhere over here the velocity is negative. So what's crazy is when I first started, he chucked the ball, and it turns out this will be the initial velocity. You don't have to know that. This can be a very approximate. So he chucks it with this initial velocity. Boom, he throws that ball. And then what's happening? The ball is slowing down. The ball is getting, so look at the tangent line. It's got a strong velocity, strong, weaker, weaker. It's getting flatter and flatter until it hits 0. So this is the velocity decreasing. The slope of that tangent line decreasing. Then it actually hits 0. The ball is frozen in time. And then what happens? It's got a really weak negative, more negative, stronger negative, negative, negative. So it's actually doing this. It's getting more negative over time. So it's a straight line looking like that. That's pretty crazy. Now can you compare that to the acceleration? Well, what's the acceleration? It is the second derivative. This is huge. It's the second derivative of the position function. Or it's the derivative of the velocity. Or we just say it's the a of t. So you got to know all that notation. So first derivative is velocity, second derivative is acceleration. Well, what does that look like? Well, it's actually the slope of this tangent line everywhere, the instantaneous rate of change of velocity. So what is going on right here? Well, it turns out, for all you physics gurus out there, it turns out that the acceleration is gravity. Maybe you recognize gravity right here. But let's go ahead and find it. Maybe we'll do a little cheat here. If this is the position function, can I find the derivative? Sure. What is the derivative? Is just what? Take the power rule. We got negative 9.8t plus 18. So that's what's going on here. If you graph this line, it's actually going down. The slope is negative 9.8. So what does that mean over here? Well, if I took the derivative again, what's the derivative of this? The second derivative, or the acceleration, is just negative 9.8, and that's a constant. It's a flat line. So that is gravity right there. It's a constant. It's always pushing down on us, and that's why the ball comes back down. So this is position, velocity, acceleration. So a couple of things I'm going to ask you here. I'm going to ask you all kinds of stuff, and you really got to practice them trying, because I'm going to ask you a bunch of different style questions here. But if I ask you to find the velocity at time 2, so at 2 seconds, what's the velocity? So you use this first derivative here, blah, 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 plug in 2. It looks like you'll get something like negative 0.6. What are you going to label this thing? Well, time doesn't change in this. Oops, I already wrote it. There's time. It's always with respect to time, but what is the y-axis in velocity? Remember, velocity is the rate of change of position. So if that was in meters, this is meters per second. So it's in meters per second. So really, this would be negative 0.6 meters per second. So that's kind of cool right there. Gets kind of weird, though, when I start to think about acceleration, which is the derivative of the derivative. So it's still time on the x-axis. So we're still doing seconds. But what is this? Well, this is the meters per second from velocity per second. Isn't that crazy? It's the change in y, which was meters per second, over x, which was seconds. So how we write this is meters per second squared. So if you're really into the science stuff, you recognize that. Acceleration is meters per second squared. You could write meters per second. I guess that's okay. But really, that just means meters per second squared. That's what we're going to use for acceleration. So if you had to find that, in this case, as a constant, it's always negative 9.8. There's gravity. It's negative 9.8 meters per second squared. So that's pretty cool. Another thing I'm going to ask you on is speed. Well, what is speed? Speed is velocity. It's the same thing. Well, you're like, well, why do we have two words for it? Well, there is a little difference. Velocity is how fast. Speed is how fast. Speed is the absolute value of velocity. Oh, see what I did there? Just put the absolute value sign on that. Oh, I didn't mean to. It just worked out. It's the absolute value of velocity is speed. So if I were to graph the speed, it's the same thing, but it can't go negative, so it just go womp, just like that. There is the speed graph. So if I ask you what's the speed, even if it was a negative, you would just give me the positive of that. And I want the positive of it for how fast is it going. So velocity is important because it shows direction. That shows you if it's going up or down. So if it's a negative, it's going down or it's going left. If it's a positive, it's going up or it's going right. So you can see there's the negative, there's the positive, showing you if it's going up or down. Same thing will happen with left or right. Excellent. All right, let's take a look at some particle motion. So, very common problem here we're going to see a lot of. So we've got this particle, and what we're doing is we're putting this on like the x-axis, or it can be the y-axis, but essentially you've got this particle here, and I drew an axis or a line, any kind of line, and the particle's moving like left and right along this line, or it can be up and down. A positive would be right or up, and a negative would be left or down. And I'm giving you the function that represents its motion over this time. So the x of t would be the position of the particle, and this is only for t is greater than 0. So a couple big vocab words here, and this is a new one. First one's going to be displacement. Well, what does displacement mean? So this thing may move left and right, but as it moves left and right, I want to know where did it end up? Like how far did it go? Did it go way right, then way left? I want to know its total displacement. I want to know how far did it move. So what we're looking at there is we want to say, okay, from time 0, so when time is 0, how far did it move to get to time 2 in this case? So I'm looking at how far did it move. So in this case, I'm just finding the x of 2, which plug it into this equation would be what? 2 cubed minus 4 times 2 squared plus 3. So the x of 2 is what? When I plug 2 into this equation, I'm going to get 8 minus 16 plus 5. What is that? Negative 5. Is that right? And then compare that to the x of 0. So what is the x of 0? Well, if I plug 0 in, that's nice. 0 cubed minus, that's going to be 0. It gives you a 3. So the total displacement is it went from negative 5 to 3. So how far did it travel? It traveled negative 8. And we're talking about units. We're on the coordinates, so it's just units. Negative 8 units. Or it went 8 units to the left. It started at negative 5. Or I'm sorry, it started at 3. Whoa! I got the order's important here. It started at 3. It ended at negative 5. So it went 8 units to the left. So definitely, you got to start with this one first. Excellent. Now, how does that relate to average velocity? So I want to know, okay, I can see its position change. How fast was it going? So we've been doing this average velocity So I'm looking at what? I got to say the x of 2 minus the x of 0. So it's change over time. So I'm putting time in this one because I'm looking at velocity. And what is the average rate of change here? It went from x of 2, do we have that as negative 5? At 0, we're at what? We're at 3. And we are taking that over just 2. So I'm looking at negative 8 over 2. Or what is this? This is going to be negative 4 units per second. Time is in second. Excellent. So at the average velocity from 0 to 2, it's traveling negative 4 units per second. And that makes sense. Each second does negative 4. That's why it went negative 8 total. So that's average velocity. How's that different than instantaneous velocity? Well, now I want to know how fast is it going at that exact moment in time. So anytime I want to do that, I'm going to do x prime of 4. And that's great. So what is the derivative? Let's put the derivative up here. So we got x prime. And the derivative is just going to be 3t squared minus 8t, and that 3 is gone. So plug your 4 in there. We're looking at 3 times 4 squared minus 8 times 4. Clean this bad boy up. What are we going to get here? The instantaneous velocity, I've got 16 times 3 is 48 minus 32. Is that 16, I hope? Slow. I was a little slow on that one. 16, and let's label this. It's a velocity, so it's a rate of change. So we're doing the same thing. This is going to be units per second. Excellent. So that's the rate of change at that moment in time. So it can be way different than the average, but it looks like at 4 it's going 16 units per second. Great. Can we find the acceleration? Sure. Remember the acceleration at 4 is just what? It's just the second derivative. So we got to be good with both the types of notation here. It's a second derivative of this at 4. And can I put the acceleration up here? Let's take the derivative again of this thing. So it's going to be what? 3t squared turns into 6t and minus 8. So there's the acceleration. And if I plug a 4 in there, that's just going to be 6 times 4 minus 8. Boom. So put that together. That's 24 minus 8. And again, oh, I got 16 again. That's interesting. Now, acceleration is interesting to label because I'm looking at a rate of change. So this is what? It's the rate of change of the rate of change. So it's actually 16 units per second, which would be per second squared. Boom. I'm looking at that right there. Fantastic. That's great. So can you describe the motion of the particle? I think in this case, it's easier to look at the graph. So I went ahead and graphed this in the calculator and put it over here. Sorry, let me move some stuff out of the way here. Oh, not that. I don't want to move that out of the way. Oh, gosh. All right, that's good enough. So let's see how this, let's describe the motion. So I graphed it. So I went from, I think, negative 10 to 10 on the y, and I'm just showing the first 5 seconds. So this is definitely time over here, and this is just going to be the units on this. So it started at 3. At time 0, we know it's at 3, so that's cool. We also know at time 2, didn't we know it's at negative 5? So at 1, 2, that's negative 5. So we know some points here. What's interesting here? So what's going on when the position of the function is going towards 0, he is moving left. So the particle, remember this particle up here, was actually started off moving left. So it's going left, and it's going to continue going that way until it reaches down here. This would be the farthest left it got. This is the position. And what's the velocity at this point in time? Well, it should be 0. Remember, the slope of this line would be 0. Pretty cool. Then the particle started to move back up. I'm sorry, in the right direction. It's moving right, right, right. So can we check some of our other answers? Does it look like from 0 to 2, so from 0 to 2, if I drew the secant line, this is what we found the slope of. Does that look like it's negative 4 units? Yeah. It looks like it's negative 4 units. Do we look at the instantaneous at t equals 4? So 1, 2, 3, 4. So what's that mean? The slope of this line is 16. That's pretty cool. And then the acceleration would be the second derivative of that. So the derivative of this straight line, turns out that that's a straight line with a slope of 16. You're going to get 16 again. That's super cool. Man, I hope that makes sense. It's going to take some time. We're going to practice these. I got a ton of practice for you. You're going to be pretty excited about that. Okay, so what happens if they don't give you the equation? It's nice with the equation. Just follow some rules, know what it means. Can we look at the graph? Sorry, can we look at the graph and see what's going on? So I'm giving you the velocity graph. So this is the velocity of a particle moving on the coordinate line. So we got the velocity, and again over time. When does the particle move right, move left, speed up, slow down? So this is hugely important. So if I'm looking at velocity, what's going on with my velocity? My velocity is decreasing, and then this would be a velocity of 0. So if your velocity is positive, you're moving right. So it looks like it's moving right from what, 0 to 1 second. So it's moving right. Even though it's slowing down, it's still moving right. It's positive. Your velocity is positive. So it moves right when your velocity is positive, equals a positive. That's when it moves right. When does it move left? Well, when your velocity is a negative. So it's moving left, it's picking up speed, it's moving quicker velocity to the left. This doesn't mean it stopped and turned around. This means it's just slowing down. The velocity is actually slowing down. So all the way to here, it's moving left. That's pretty hard to think about. So from 1 to roughly what, 4.75, it is moving left because the velocity is negative. Then what happens? Boom, it's moving right. So it moves right here. So it's back to moving right. Let me come over here from approximately, what would we say, 4.75 all the way to 7. It's positive. So it's weird. You're moving right, but it's got a slow velocity, kind of picking up speed, but then it is losing velocity back down here until it has no velocity. So that's hugely important. So when is it speeding up and slowing down? Let's come back to this one because I want to do the next one. I think it's going to help us with that. So when is the particle's acceleration positive, negative, or 0? So remember, acceleration is the derivative of this. So I can find the derivative. What's the derivative of this line? Well, it's the slope of this line. Like any point on here, the instantaneous rate of change is that slope. So what am I saying the slope of this line is? Well, it's down 2 over 1. So this whole part from here to here, it's down 2 over 1, down 2 over 1. I'm going to graph it. Your acceleration is actually negative 2. So let me get a different color here. Let's do green. So from 0 to here, it is actually negative 2. Then what's your, whoa, is that thick enough? Then what's the acceleration? It's the slope of, it's the instantaneous rate of change of this. Since it's the straight line, it's just the rise over run here. So this is going up 1, 2, 3 over 1, 2, 3, 4. So it's 3/4. So from here to here, it's at 3/4. Again, this is the acceleration. Ooh, that's supposed to be a straight, nice flat line. And then what happens here? It's down 1 over 1, so your rate of change is negative 1. So I just graphed the acceleration. Why'd I do that? Well, when is it positive? The acceleration is positive from 2 to 6. So it's positive from 2 to 6. When is it negative? Well, it's down here at let's try that again. That looks bad. From 0 to 2. And it's also negative from what, 6 to 7. These are the times where it is negative. Is there a time when the acceleration is 0? In this case, no. I don't have a place where the derivative is 0, so there is no place where it has no acceleration. So how does that help me with speeding up and slowing down? Well, if I have velocity is, well, you can maybe tell the velocity is what here? The velocity is just slowing down. It was a velocity of 2, I'm going towards 0. But this is really weird. What's happening here? My velocity is actually picking up pace right here. I'm getting more velocity. Now, granted, it's in the negative direction or the left direction, but I'm actually speeding up. So I'm sorry, I'm kind of going out of here, the order here. From 1 to 2, I'm actually picking up pace in the negative direction. Now here I'm slowing down. Isn't that crazy? I'm getting less negative until I hit 0. Uh-oh, check this out. What's going on from here to here? Again, I'm speeding up from that, what do we say that was, 4.75 roughly? To what, 6? Because I'm getting more positive, right there, and then I'm slowing down from here to here. I'm getting less of a velocity. So you can think of it like that. Or if you can think about it, a good little cheat right here, and I think I put at the bottom, is if your velocity and acceleration have the same sign, the object is speeding up. So if you can go back to, and I got a lot of mumbo jumbo, let's get rid of some of this. So if you can look at this and see, okay, where do they have the same sign? So up here, velocity is positive, but acceleration is negative. It's slowing down. Your acceleration is slowing it down. But here, check it out. Velocity is on the negative, and so is your acceleration. This is the area where it's speeding up. Here, my velocity is negative, but my acceleration is positive, so it's slowing down. But then check it out. From this point on, I have a positive acceleration and a positive. That's where it was picking up speed. And they're opposite here. That's where it's slowing down. So this is a great little trick. If they have the same sign, it's speeding up, velocity and acceleration. Or you can kind of look at the graph. Whew, I feel like I'm throwing a ton at you. Going fast, we're going to have to work problems. Like, you really just got to get in there and work problems. When does the particle have the greatest speed? So speed is velocity. So what does that mean? Well, speed is the absolute value of velocity. So really, my graph would never, if I absolute value with this thing, it would be this. This would be the speed graph. Just kind of cover up that bottom there, and it would be that. What's the highest speed possible? Well, it happens twice at 0 and 2. Its greatest speed would be a velocity of 2, and this is units per second. So double check when it says speed. I don't care about positive or negative. You got to look for in this case, they're the same, but you got to check them both. Holy cow, I talk fast. Get in that practice. The test prep is small, but really the last like 11, 12, 13 are just like test prep. They are hard. They're supposed to be hard, but I wanted to show you the answers worked out, so that's why I put them in the practice. Sorry about that. Nothing that hard on the mastery check, but I want to get you ready for the test. So give it a shot, see how it goes. Good luck on this. Peace out.